Today we are going to discuss about forces and they are, what are the forces? There will be many of them, so we can start. Don't be shy. Very nice. Now, the word bond is correct or not? No, why not?
It's just a kind of stress, not really.
You remember that when we're discussing bonds, we are saying that the bonds are divided in a few categories. We said there are metallic bonds, ionic bonds, then where there were covalent bonds, there were polarized bonds, or as your book says, polar bonds. And finally, there was one more category. Donor-acceptor. Okay, we said that these two happens only in solids and the rest happens in molecules. So let's forget about these two. We are now speaking about molecules. Which are the strongest? Probably covalent has the strongest bonds. And you know that the strongest bond was the CO bond, right? Which is in fact a bit polar, but not too much. So polar and covalent are the strong ones, and donor acceptors are rather weak. And hydrogen bond can be considered as a bond, as a donor acceptor bond. So a weak bond. So you are right, this is not very much a bond, because the bond is something strong. Here is something, a physical force that we usually call a bond. But you should remember it's a donor-acceptor bond. Electrons are coming from one of the atoms. And so A has a lone pair and the B connects. In the case of the hydrogen bond, this is most often oxygen and B is most often hydrogen. Is it possible that this is not oxygen and not hydrogen? For the hydrogen bond? At least one must be hydrogen, right? But the other one can be? F. What else? Nitrogen. N. Okay, what else? Nothing more? What about sulfur? It's just under oxygen. What's wrong about sulfur? I don't know. I'm just asking you. Just question mark. I don't know. Sulfur is wrong? Why? Electronegativity is not big enough, right? Maybe. I don't know. To be honest, I don't know. But we have these hydrogen bonds, and these are true. These are forces, strong forces that keep liquid molecules together, but only if there is hydrogen and only if there are these elements to keep the hydrogen. What happens if there are no these elements and no hydrogens in liquid? What other forces? Oh, we studied them already. Van der Waals. Van der Waals forces, or are there other called by other name dispersion forces? Well, what can you tell me about van der Waals liquids? Give me example of van der Waals liquid. Don't be shy. Okay. Liquid argon. Liquid neon. Liquid helium. What about them? What is special about them? They can be liquids only in very low temperatures. If you go temperature high, it means they are becoming gases. Why? Why the temperature dependence is so crucial? Louder. Noble gases, that's correct. True too. Water molecules are happy with themselves too, but the boiling temperature is higher. Ah, nice. So the other forces, they're not only van der Waals forces in water. That's correct. But the point is that the van der Waals forces are extremely weak. So if you go with the temperature a bit higher and the molecules have faster speed, they just go away. Next one you said? You said, just repeat. Yeah, dipole-dipole interaction. And example, as you said, is water, H2O, having strong dipole moments. I don't remember, we decided to write the dipole moments from plus to minus or from minus to plus? From plus to minus, okay. So it's a dipole moment on a water molecule like that. And these dipole moments can interact by attracting each other or by repelling each other. Turns out that this one keeps them together, this one makes them go away. But the number of this type of interaction is larger than this to minimize the energy. So finally the water molecules stay together. So dipole-dipole moment interactions are very strong. And these are extremely important. So usually high boiling temperatures. Good. What else? Gravitational force, you said? Heavy molecule is hard to become gas. Heavy molecule is hard to become gas. Yes, but you remember the reason is for that the velocity of the molecule has a mass here. And because of the mass here, the velocity will be small. So only in high temperature, the velocity would be big enough to overcome the force. So this is not because of the big force necessary, but because of the small velocity. So we fish for some other. But good, just try. Well, there are many others, but I mean, I just give you example of the ion-ion. Good example. Which is the liquid that you have ion-ion interaction? You are very quiet today. Okay. Example can be molten NaCl. Okay. If you melt sodium chloride, you get a liquid which has only ions, and you have ion-ion interactions. What would be the boiling temperature? I mean, liquid becoming gas. It will be huge because the ion-ion interaction is much stronger than dipole-dipole interaction. Well, if we have this, then kind of typical things for solutions, ion-dipole interactions. Now will be difficult part. I don't know if you have ever this, but quadrupole. Anybody heard about quadrupoles? What are quadrupoles? Yeah. Okay, so we have to study about multipoles. I think this is useful for you finally in one day. So let's have a short introduction to multipoles. Short introduction. Imagine that you have a positive charge. It can be plus or can be minus. This is called monopole. Mono means one, and pole coming from the word polarized, polarization. So single polarization side, positive or negative. When you have plus charge coupled together with the minus charge, this is called dipole. There may be E at the end. I'm sure there is. It's not in the dictionary. Quadrupole. There is, or maybe say in Chinese. No. Now. Okay, let's continue. This one and this one is simple. These are single charges. Okay. These are two opposite charges Now we are coming to quadrupole. Of course, it's not finished, because later you have octupole. And so on and so on and so on. I don't know how to call them later, and I don't know how to draw them either, but it's not the end. You can continue this story. Why is it important? Because if you have some strange distribution of charges, like that, very strange shape, very often you are too lazy or it takes too much bothering to discuss the exact shape of this, and you would be very happy to, instead of discussing the shape, you would be very happy to discuss only one point approximation to this. So what do? You take the strange distribution of charges and you represent it as a multiple series. What does it mean? Well, first, starting from this point, where will be your starting point, you calculate the distance to every charge here. So let's say these are the plus charges. And these are the minus charges. Okay. So now you calculate the vector to each of the positive charge. All of them. Okay. And now you multiply the distance to this place by the charge. You multiply it. And by doing this, you get the center of positive charge. Later, you do the same for the negative charge. You get the center of negative charge. So by finding the center of positive charge, let's say it would be here, and by finding the center of negative charge, you are finding the dipole moment. which is a vector. So instead of discussing some strange distribution of charges, you already know that this strange distribution of charges can be represented as a dipole moment. But this is not everything. You can do also different thing. You can also calculate the following thing. Total positive charge would be Q1 plus Q2 plus Qn. Then you can calculate the total negative charge would be Q1 plus Q2 plus Qm, maybe different. And finally at the end you calculate the total charge of everything as a Q plus plus Q minus. So the total charge. So what we are doing, we are just replacing the very complicated distribution of charges by simple things. One of the things is total charge of this thing, when you just take all plus charges, all minus charges and put together. Another thing is the total dipole moment. When you just calculate the center of the positive charge, you calculate the center of the negative charge, and you add them together, getting the dipole. Well, it turned out that it's a good place to continue. I think we wrote the most important one, so I can remove this one. We are going to discuss it a bit later. Good. Let's continue. So, starting once again. For the monopole, I just did Q equal K1 plus Q2 plus for the dipole, I did Q1 multiplied by R1 vector plus Q2 times R2 vector Good. Now is a good moment to define quadrupole. I started with the double underscore, whatever it may be. But we should finally understand what it may be. Q is a scalar, is a single number. Mu is a vector, is a set of 3 numbers. What will be this? What will be quadrupole? Very nice. It's a matrix. It's a 3 by 3 matrix. And we are going to define the elements of this matrix in a moment, but before we should understand. Monopole has the 0 dimension. It's a point. Dipole has 1 dimension. It's a vector. Quadrupole is 2-dimensional matrix. We say it's a tensor. So it's a 2-dimensional tensor which can be represented as a matrix. We already know that octupole will be 3-dimensional object, but I really don't know how to write octupole symbol. I'm just guessing it's B. And it's a 3-dimensional object, so it's also a matrix, but a 3-dimensional matrix. So 1, 2, 3, 4, 5, 6, 7, 8, 9 digits, then 10, 11, 12, and so on. 27 numbers. And we say it's a 3D tensor. And you cannot say it's a matrix anymore. Okay, let's come back to a quadruple for a moment. Quadruple will be given by alpha xx, alpha xy, alpha xz, alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz. 9 numbers. In fact, turns out that it is not really 9 numbers. And the reason for this is that this one and this one has the same value. It's a symmetric matrix. If it's symmetric matrix, it also means that this one and this one, and also this one and this one would be the same. So finally, there are 6 independent numbers to be found. How to find it? Well, very simple. Alpha xx will be given, no, I need some more space. So I remove the octupole for a moment. So I start here. Alpha xx will be given as exactly the same like dipole. Very similar definition. So we start q1 x1 x1 plus q2 times x2 times x2 plus qn xn xn plus q1 x1 x1 plus qm xm xm. What would be given alpha xz? Similar. Start with q1 x1 z1. So you see xx xx xz xz. M. Very simple to define. Where is the names are coming from? Let's try to work on the names a bit. Mono, di, quadru, octu. This one means 1, this one means 2, this one means 4, this one means 8. But this one is just 2 to the power 0. Here is 2 to the power 1. Here is 2 to the power 2. And here it's called 2 to the power 3, right? So you see that the next pole would be called something whatever is 16. I think it's called hexadecupole, something like this. Who cares? Yes. Okay. Now, when I'm here and I have an electric charge and I want to calculate interaction of myself with this strange distribution of charges, I should calculate the distance to every white point and the distance to every red point, calculate the force and the energy for each interaction and sum it together. If the number of these points is very large, it can take a long time. But it may happen that this is not point distribution, but it's a smooth distribution. Like electron was a cloud. It's not just point, 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 point. It's a cloud everywhere. Then you don't do summation, but you do integration. And so that may be a complicated integral to calculate. So instead of doing this, it's much easier to represent this strange distribution of charges as a series. You say, what is the monopole? So what is the total charge of everything? What is the dipole? So, and where is pointing out? So what is the total dipole of everything? Next, you say quadrupole. What is the quadrupole distribution of charges? And turns out, if you look at the quadrupole, that is a matrix. Now, this matrix can be diagonalized. You probably still don't know what it is, but it means that, okay, I skipped this, no. Right. Anyway, you can make the series and you can find the distribution of charges in the series. And then when I calculate the interaction of this object with this strange distribution of charges, I just calculate charge, then I calculate charge dipole, then I calculate charge octupole, and so on and so on and so on. So it's much faster to do this that way. Good. So, but the point is, if you do this multiple series, you find that the charge is the largest in contribution. Dipole is smaller contribution. Quadrupole is smaller. Octupole is tiny. And hexadecupole is very, very small. It means that you need only few terms of this multiple expansion to calculate something accurately. So most of the cases, people are contributing only monopole and dipole at the end. Sometimes people include quadrupole. Almost never people goes to octupole. You can just see few cases. Good. So you have the basic ideas of the multiple series. Now we can calculate what is the interaction between two charges. So the energy of interaction of two charges, of course, is the charge 1 multiplied by the charge 2 divided by the distance between these two charges. Good. Now we are going to calculate, that was the charge. Let me write it once again. This is the interaction of charge 1 and charge 2. Now we are going to find the equation for interaction of the charge with dipole. To do this, we assume that our charge is here and our dipole is somewhere here. Now we assume that the distance between the plus and positive charge, the negative and positive charge of the dipole, is r. And we also assume that the charge here is some q. Here would be plus q, and here would be, of course, minus q. Now, we also assume that the distance to the center of the charge separation from this charge is a big R. And you see that also things will be depending on this angle, alpha. So now we can calculate the interaction for the dipole and charge. So this interaction of a charge and dipole would be nothing else like the interaction of the charge and the plus charge plus interaction of this charge and the minus charge. Okay. Now we have to calculate what are these two. This is, of course, equal to Q times Q over R plus you see that here many things can be simplified. For example, you can take the Q and Q outside, and you have that it is just 1 over R Q Q minus 1 over R Q minus Q. Okay, now we have to calculate what is the R. Clearly this is this distance. And clearly this is the same like R plus I have blackout. Let somebody tell me what it is. Can you calculate the distance between the Q and Q? This is a simple mathematics, right? Calculate the sine of the angle and so on. Can be simplified? I think this one can be a bit simplified. There's already this, yeah. Good, thank you. Good. And for the other one, we would just have here now, R is very big. This one is very small. So you can take R outside. And you would get here 1 plus R square divided by 4 R square plus R over R cosine alpha. Good. Now for the other one, for the R Q minus Q, there will be similar formula with the only difference that you get here cosine of alpha. And finally there will be minus here. Correct? Good. Now we have to plug this thing here. And you see that this will be equal to Q over R 1 over square root 1 minus R square 4R square plus R over R cosine alpha minus R square 4R square minus R. Here's plus, of course. Plus minus R over R cosine alpha. Good. Now we have to find common denominator, so multiply these two things together, and later you get the difference of two things above, and we are going to calculate this difference on the next class. Turns out that if you take this difference of these two square roots and you expand it in the Taylor series, this thing will be approximately equal to 1 over R. So we get here the formula of QQ over R square, and that will be the formula we want to use. But to do this, we should finish this mathematics on the next class. That's very simple. So on Tuesday we'll be continuing. Thank you very much for today.